All right, so the standard normal distribution, again, we're standardizing this to force the mean to be 0 and the standard deviation to be 1. Here, down here you see that z is distributed normally with a mean of 0 and a variance of 1, which of course means the standard deviation is also 1. Okay? Now, what we're finding here, if you think about what you're doing, you're taking a score, that's what the x here is, okay? We've got x, and we are subtracting the mean from it, okay? That's going to tell us the distance away from the mean, right? For each score. And by the way, this is something that's kind of unique to these z-scores. A lot of the statistics we calculate, we're taking all the data and coming up with one number, like the standard deviation or the mean. But in this case, you're going to get a separate z-score for each data point. All right, and we'll see that a little bit later. Okay, so we're finding the distance away from the mean, and then we divide by the standard deviation. And what that tells us is that tells us how many standard deviations each score is from the mean. Okay? Now, let's illustrate this with a couple examples. Okay? So here I have two different performances in a triathlon. Okay? Triathlon has a standard distances that you have to run and bike and swim, but due to different conditions, maybe the weather or the wind or whatever, the times could be very different. All right? So let's say that in one race you ran, the mean time was 12 hours and the standard deviation was 1, and it took you 14 hours. Okay? So if I were calculating z for this, okay, z is x minus mu over sigma, right? So I would take 14 minus 12 over my standard deviation 1. Okay? Well, that's 2 over 1. And that means that my score of 14 is exactly 2 standard deviations greater than the mean. Okay?
So for the example that the guy did, it was like 0.5 standard deviations from the mean?
Exactly, yes. Okay? So, and actually if we think about this, this can help us figure out kind of where we were in terms of the pack, right? Because you guys know, if you look at your bell curve, if zeros are mean, we go up 2 standard deviations, okay? You guys know that 95% lies within 2 standard deviations, and then there's that other 2.5% on either end. So here's -1 and -2. So this is, 2.5% to the left of here, and we know that all of this is 95%. So, frankly, we didn't do so hot. Now, if you finish, you're doing great in my book, but compared to the rest of the field, okay, you were in the 97.5 percentile, okay? Meaning, 97.5% of the other people finished faster than you. Okay? Now, here's another one where the mean was 14 hours, so 2 hours slower, and the standard deviation was an hour and a half. Okay? So maybe the wind or maybe the weather was bad, so the really good ones, it didn't affect their times that bad, but the people who are less experienced, it probably impacted them a lot, so we ended up with a much more spread out field in our race. Okay? So we have here the mean of 14. So if I'm finding the z-score for 16, our time this time, 16 minus 14 over 1.5, okay? That would be 2 over 1.5, which is 1 1/3. Okay? Now, that means our time this time was only 1 1/3 standard deviation slower than the mean. So, how would you say we did compared to our first time? Yeah, we did better compared to the pack, compared to everyone else. You might look at your times and be like, man, I was 2 hours slower. But you can't just do that comparison, because compared to the entire group of people doing it, assuming the groups of people are the same, it's just the conditions impacting our times, you could say, you know what, my time was slower, but I actually performed a little better compared to everyone else. Okay? Because I was only 1 1/3 standard deviation slower than our mean time. Okay? So that's one use of this. Okay? Yes?
So 97.5 in the previous one, it gives us that we were lower the percent of 97.5 people who like finished the latest.
Yeah, in this case it meant 97.5% of all the people racing finished faster than we did. So we were kind of slow. Okay? Whereas this time, if you looked at the bell curve again, it doesn't lie right on one of our standard deviations. Here's 1 and 2. 1 and 2. Okay? We would have been somewhere around right here, 1 1/3. Okay? So only this many of the people finished faster than us. Okay? Which I don't know what percentage that is off the top of my head, but it is better than the 97.5 that we got in the first time. Okay? By the way, we call this the percentile. We'll talk about that more in the next section of the book that we look at. All right? So, look at some specific z-scores. All right? Go ahead and take a minute. Use the formula that you're given up there and find the z-score for each of these 3 scores. Okay, so what do we get here for 20?
Negative 0.629.
Negative 0.629. Okay. Does that make sense? Why does it make sense that it would be negative?
Because it's smaller than the mean.
Yeah, we're below the mean, right? And it makes sense that it's between 0 and negative 1, because we're only 1.8 away from the mean, and the standard deviation is 2.86. Okay? So think about your values. Make sure your answers make sense. All right? Here, 24 is only 2.2 above the mean, so it's going to be less than 1, right? But it is going to be positive. And what do you get for that exactly?
0.769.
0.769, okay. And then how about for 26? 1.47? Okay.
Are you okay if we express them in fraction form, or do you want us to do the decimal for our answer?
Well, actually, you'll see why in a second, why we're going to want the decimal,
Okay.
all right? Because actually, if we look at the, and I realized I rounded these improperly, so this should be, I just cut them off rather than rounding each of these. So this should be negative 0.63, and this should be a 0.77. Okay, and this last one here should be 1.46. Okay, but I'm showing you this table here. This is a table that the IB actually doesn't require you to be able to use. Anything like this that you're going to be doing, you'll be doing with your calculator, okay? But it is useful, and if you take any kind of stats in college or whatever, you're most likely going to be working with a table like this, okay? Or you juniors, if you take AP stats next year, you're definitely going to be working with a table like this, okay? So I'm going to skip the negative one for the moment, because the negative, you'll notice all these z's are positive, okay? So let's go to the 24, the 0.77. I want you to see how we get our value that we need, okay? We need 0.77, and you'll notice this left column, okay, has the ones place and the tenths place, okay? across the top row is the hundredths place. So we can, if we round all of our z-scores to the nearest hundredth, we can use this table. All right, so for 0.77, I'm going to come down here to the 0.7, and then I need 7 100ths as well. Okay, so now I just come straight across here, and straight down here, and the probability, notice the probability I'm finding, the probability that x is less than 24 equals 0.7794. Okay? So that's how we can use the table. And it actually doesn't matter what the original mean and standard deviation were. If it has a z-score of 0.77, it's going to be 77.94% below it.
Sorry,
Mhm.
how did you go 24? Oh, gosh.
It was the original score.
How did you know it was 0.07?
Well, I need 7 tenths and 7 hundredths, right? So here's the 7 tenths.
Okay.
All right, this bottom one here, 1.46. I'm going to come to the 1.4, and then I need 6 100ths. Okay, so I'm going to come over here, and then down here, and the probability that x is less than 26 equals 0.9279. Okay? Now, I had these from smallest to largest, but I wanted to leave the negative one to the last because we have to think a little bit about this one. Okay, so here's our bell curve. And we've got 0 right in the middle, right? And here's negative 1. So negative 0.63 is going to be somewhere around here. Okay, negative 0.63. And I want this area to the left of it. Okay? However, our table does not have any negatives. So, does anyone have any idea of how we could use the table still?
Subtract 0.63 from 1 and then find it for 0.7. 0.37.
Okay, that's not a bad thought. We are going to do something similar to that, but not in that way exactly. What do you think?
I know we could do the probability, the 1 minus the probability that x is greater than positive 0.63, but I don't know how to do that, so.
Okay, let's write down what he just said. He said the probability that our z is less than a negative 0.63 is going to equal 1 minus the probability that z is less than a positive 0.63.
Or would be greater than, or?
Well, that will give us the probability that it's greater than, right? Now watch this. This is where your idea is good, okay? We've got positive 1 here, and here's the positive 0.63, right? Because I have symmetry in my normal distribution, this area above positive 0.63 is going to equal the area I want below a negative 0.63. Does everyone understand that? Okay. So what I have to do is, if this area equals this area, then I can find this area by doing 1 minus the probability that it's less than that. Okay? So, if I come over here and I look at 0.63, Okay, here's 0.63. All right. That means all this area down here is 0.7357. Okay? That's the area below this 0.63. If I want the area above it, though, I need to subtract that from 1. Okay? So 1 minus 0.7357 is going to be 0.2643. Okay? So for the negatives, the simple rule for finding it when you have a negative z-score, if you're using the table, you just do 1 minus the value under the positive z-score. Okay? We're using the complement principle there.
So we did 1 minus 0.7351 in order to find the 2.6.
Yes. Yes. Okay? Yeah, we're doing 1 minus that to get what we're looking for. Okay? Now, like I said, for the IB, any of this stuff that you're doing, you would just use your calculator. You would use your normal CDF.
Are we gonna go
Okay.
over how to do this, or
Yes. Yes. So, let's, man, come on. Alright. So, let's do this using the normal CDF. Grab your calculators. And notice here on all of these, because we're doing the standard normal distribution, for all of these, your mean is 0 and standard deviation is 1. By the way, when you hit normal CDF and it pops up that little menu where you put in lower bound, upper bound, did you notice what they put in by default for your mean and standard deviation? 0 and 1. Okay? So they expect that you're going to be doing this relatively often. Okay?
Will be our lower bound 20 and like.
Well, the lower bound, if we think about this, okay, here we can do the same thing that we did before with our lower bound. All right, I'm going to get a video going here so you guys can see this in action. All right, so we've got this. Okay, and I'm going to clear this out. So I'm going to do second distribution, and I need to do the normal CDF. Okay? Now, I want to do up to a negative 0.63, right? It's 0.63.
Negative 0.62.
Okay, 0.6.
I mean, we changed it.
Okay. So the lower bound, I could just make like a negative 10 or something. I mean, that's going to be 10 standard deviations below the mean. Okay, or you can still just do the negative 999, whatever you want. Okay, but then I want the z-score to go up to a negative 0.63. Okay, my mean is 0 and my standard deviation is 1. Okay, so I put that in, and you'll notice we get that 0.2643, just like we did with the table. All right, but we get the same thing there using the calculator. Okay? So, same stuff we were doing the other day, it's just the mean and standard deviation are 0 and 1 every time. Okay? Now, another thing that this is used for that is where this really gets useful is when you know the percentages and you know the scores, but you don't know what the mean and standard deviation are. Okay? And this I've seen a whole bunch of times on the IB exams, this type of a thing. Okay? Here, we have a score of 30 that has a z-score of 1.2, and a score of 20 has a z-score of negative 0.3. So, I know, just by thinking about this, I know that my mean is somewhere between 20 and 30, right? Because 20 has a negative z-score and 30 has a positive. I also know that it's going to be closer to 20 than it is to 30, right? So there's a couple of ways that we can figure this out, but probably the most direct way here, the simplest way, is let's think about our formula. Z equals x minus mu over sigma. Okay? So, using our first bit of information, a score of 30 has a z-score of 1.2. How could I write an equation to represent that?
1.2 equals x, or 30 minus, yeah.
30 minus,
Over theta.
okay, 30 minus mu over sigma. Okay? So I have two variables here, which is okay, because we have more than just one piece of information. We also have the fact that a score of 20 has a z-score of negative 0.3. So,
Are we gonna make them like equal to each other?
Do a system of equations.
yes, we're going to do a system of equations, okay? So a z-score of negative 0.3 is going to equal 20 minus mu over sigma. Okay? Now we can solve our system of equations. Okay? Negative 0.3 equals 20 minus mu. Okay, if I do the same idea with this, or I'm sorry, negative 0.3 sigma, I should say. Sigma. And then for this, 1.2 sigma equals 30 minus mu. Okay? And you know what, to solve this, I'm going to solve this by combining the two equations. I'm going to multiply the first equation by a negative 1. Okay? Because then I'll have a plus mu and a minus mu. Okay? And that cancels out. So now I have that 10 equals 1.5 sigma.
Wait, we multiply the first one by a negative?
Yeah, negative 1. However you guys like to solve your system of equations, just go for it, okay? But now 10 divided by 1.5, okay? It's the same as 100 divided by 15, which would be 6 and 2/3. Yeah. Okay? Now, an alternative to using the system of equations, you're kind of thinking about it the same way. But if you think about it here, a difference of 10 is equal to a difference of how many standard deviations? 1.5. That looks familiar, right? That's where we got to eventually. It takes a little more logic to think it through carefully. So that's why I said the system of equations is a little bit more of a straightforward method. You've got your formula, you plug it in, solve the system. But if you think about it logically, hey, those are 1.5 standard deviations apart, and they're 10 units apart. So now I know what the standard deviation is. And then you can go back and find your mean some other way.
But we can just use
Okay.
but we can just use the system of equations.
Yeah. Either way you like. Okay? All right. Have a great day, guys. I'll see you tomorrow.